Okay, so complex numbers, and what are they? Trying to understand what complex numbers are is futile, really. Under the circumstances, it's better to think about making sure that you know why we do it, and secondly, how they operate. Okay, really, it's the nature of a complex number is not something that is easy to just describe. It's just how they operate, what they're made of, and how they operate. And they're made of these two pieces primarily, real numbers, and then mixed with the one single extra thing to begin with, and that's the imaginary unit. Okay, so regular unit, real unit, and imaginary unit. So this is what we start with. And then we just carry out algebraic operations as if they were the numbers were real, just without intermixing, without asking ourselves what is the meaning of 1 plus I. Okay, it's not that we do. It now from the point on. It is from this point on. It is meaningful, but we don't say what it is. Okay, we don't mix them up. It's the attitude that you've seen before whenever you deal with either X's and Y's, or you're dealing with units, inches and feet. Well, inches and feet, you can that's the thing. So it's inches and pounds. Okay, pounds. Okay, so inches and feet. You can translate inches into feet and feet into inches. Okay, so the analogy is more with inches and pounds. So which is you know that you don't add inches to pounds. But in a way, especially with the background that we've had with vector algebra, we did mix up, for example, the data that we may have dealt with in 2 dimensions was not necessarily homogeneous. Okay, so for example, you have vector AB. Remember, so it could be referred to literal location on the plane, or it is a literal location, literal 2 populations. But why cannot it be? Remember the vectors. The one example of vectors we had was with the mixtures of different types of coffee. So then A and B could be could be dollars, and these could be pounds. Okay, in which case, and then you can write it as this. You can write it as if it is A. 1 plus B E2. Okay, so then the situation is really described by 2 numbers combined together, each of which is not to be they're independent. Okay, they cannot be one cannot be expressed in terms of the other. Okay, so you just keep them together, and in a kind of formal way, you put a plus between them, as if it is a possibility. So once again, what does it mean? 5 pounds plus $3. It seems meaningless if you try to actually carry out the addition. Okay, but you don't. There is no need. They're just formally put together because that's the describes a certain state of affairs for whatever it is. Just like you can have miles in both directions, but you can also have if you're dealing with data. They might be entirely of a different nature. Okay, so that's very good example that if they're different nature, one are numbers and one are not. Number is imaginary unit, which is not a number in the sense that we have used to. Fortunately, other than that, we see that the behavior is of those formulas that we produce is the same as before. The only things for us to remember is how we handle the imaginary unit, and these are the 3 properties that we put forward. Okay, so number 1, it's not a real number, so not to be mixed, and so it's not like X, which is also a real number. It can participate in all algebraic operations with real numbers, but secondly, I squared is equal to -1. So certainly this 1 and 2, but 1 and 3 are interrelated. Okay, so incidentally, since I is not a 0, then you can divide by I, hypothetical. Okay, so these are the operations that we've had. Okay, so once again, imaginary I is the imaginary unit. And then multiples of imaginary unit will be real multiples, okay, so naturally I times I is also a multiple unit, but the end result is not a number that is imaginary, but rather it is real, okay, so that's not it. Okay, and then what we have is that our numerical system for now is a mixture of these two, all the real numbers, all the imaginary numbers, except the only exception is this one, so that's the same one. Okay, so among imaginary, the axis of imaginary numbers, actually, there's one number that is real, that's a zero. Okay, so then the next one we're gonna attach them to each other, just as we did before. So quadratic equations, then either it gets a trivial equation as this and produces imaginary numbers in this fashion, just take square root, or as we're gonna do in a minute, we do the quadratic formula. Okay, so that's where you have the square root there, the quadratic formula, which is regularly produces imaginary numbers. Okay, so once again, how do we execute addition? Once again, apples with apples, oranges with oranges, and so it's just factor it out. So 5i plus 3i gives you 8i. Okay, so just like 5x plus 3x. Okay, so inches plus inches, apples plus apples. But if you intermix inches and apples, that's fine. So for example, what is it? Yeah. So yeah. Okay. So if I go with 5 inches plus 3 apples, what's the meaning of it? The answer is it is still 5 inches and 3 apples. Okay, and now we have multiplication. Multiplication of imaginary numbers, as you can see, produces a result that is you can multiply by a real number, which produces once again imaginary number. But if you multiply two imaginary numbers, you will get a real number, which is comes from requirement number 3. 5i times 3i. As I said, you are allowed to do the algebra as if you're dealing with real numbers, the usual numbers, and then you can rearrange all the branches the way you want, and so you end up with I squared, which is -1, and so the answer is actually -15. Okay, so that allows us to cancel. That's interesting. So if you can divide among imaginary numbers, once again producing real numbers. If you 5i divided by 3i, I can be canceled out because it is an imaginary. It's not a real number. So cell phones and laptops, please. Cell phones and laptops. Don't use them.
Take my notes on.
Well, then you gotta somehow do it in such a way that it didn't look like you were browsing the web. I don't know what the trick is, but just try not to be a distraction. Okay, okay. So divide I by I, you end up with 1, and so you end up with 5/3. But just as 5i times 3i produces a real number, so that's the indication that we are in a bad place. We are in a bad place of doing there is no imaginary algebra. Okay, there is no imaginary algebra because you start doing algebra, the usual one. The addition is fine, the addition subtraction is fine, but multiplication division produces real numbers, which means that the only way for us to have the algebra that is proper is to actually combine them together. So, and that's what we call a complex number. Combine real and imaginary numbers into one system, and then there would be no trouble that going back and forth from real to complex and so on. So once again, as I pointed out, that's really the where things come from, and they remember where it came from. It is the characteristic equation. Okay, the characteristic equation. So remember, to find the eigenvalues is equal to 0. It is a quadratic equation for dimension 2. Quadratic equation. Quadratic equation has a quadratic formula, and it has a square root. Okay, it has a square root, and that square root is the square root of the discriminant. Remember the discriminant, and so it can be easily be negative, in which case we automatically produce in that place of the quadratic formula will produce the imaginary number. Combined together, however, we automatically end up with a combination of real and imaginary numbers, this, and that's what we call complex. Okay, so if we're lucky, we end up with, using quadratic formula, we might end up with a real. We can end up with imaginary or the neither. Okay, so what make it neither? When b is not equal to 0, that means that there is a real part, but also the discriminant is negative, which means that the square root will produce, as it does over here, produces an imaginary number. Okay, so together, we don't want to anymore think of this as a kind of a formal or kind of a push thing together into one combination of two totally different numbers. We want to think of it as one number. And so then we execute algebra of these complex numbers. Okay, so then a plus bi, that's what it is. That's what we call where a and b are real and I is I. Okay, so then that's what's called a complex number. Okay, so once again, then adding complex numbers is really the same as adding real with real and complex and imaginary with imaginary, as we would do with apples and oranges right here. Okay, as you would do with x's, you have x's in numbers. 5 plus 3x, 2 plus 4x. You combine numbers with x's separate, in x's separately. Okay, so then you end up with 8 plus 7x. Once again, not trying to complete the computation any further. That's all there is. There's an 8 and there's 7x. That's it. So we stop at as is. And even though, you know, the algebra is similar, even though by its nature, x is still a number. It just happens to be unknown. Okay, so I definitely is not a number, but nonetheless, we'll look at it is total similarity. I don't know, not similarity more than the similarity, but almost it's identical pretty much. Identical computation, look at it once again, apples, oranges, numbers and x's, numbers and i's. Okay, so and there, as you can see, everything carried out in exactly in the manner that I described. So the set of complex numbers, once again, it contains the reals. Into the reals with R and this complex with C. Okay, so once again, just like what is the meaning of a real number, you might be confusing, other than just explaining that real number might be referring to a length of objects. Okay, and complex numbers may not have such a nice explanation, but nonetheless, the real numbers to be mathematically treated, they are to be understood as infinite decimals, for example, in which case you have to speak of sequences, in which case you have to actually use calculus in order to explain the algebra with them. So complex numbers are actually simpler if you already have real numbers available. Then building complex numbers from them is a breeze. Look at it. We are relying on real numbers algebra. Okay, so to be explained beyond addition, let's go beyond addition, and then so this is still addition, and this subtraction is easy. Multiplication requires extra work. Okay, so let's take a look at this. Multiplication of two complex numbers requires extra work, but you still do the still expand as if these are, doesn't matter what these are. Okay, and we did already that, the same thing with vectors, so it's not entirely new. And so you just multiply 2 by 2, end up with 4 terms, and then because I appears twice, so there will be 3 terms with i's. But in one of them, the I appears twice, which means that it will become real. So 5 I squared, which is negative 1, or negative 1, which gives me 5. So this is negative 5i squared, actually becomes 5 over here. Okay, so we end up with 3 plus 5 among the real numbers. Among imaginary numbers, I have 15i minus I, so altogether I have 8 plus 14i. Okay, so that's all there is. There's some extra work to be done. It's because of the multiplication. There is an interaction between it's okay to interact. Real and imaginary numbers are actually interact very easily, right? So 5i, that's all the interaction we need. It is an interaction of the imaginary with imaginary. Okay, so that's really where the only place that something unusual happens is here. So and then you have to cancel out I squared, replace it with I, with negative 1. Okay, so division is even more complicated. Don't want to go into the details. How to simplify, you know. the point of the computation is really only turn it to the standard form. Okay, so let me explain, let me point that out. What's important, this is the standard form. Okay, so it doesn't have to be in the standard form. This is a non-standard form that through computation simplification, we have the standard form where the two parts, A and B, are explicitly present. Okay, but nonetheless, so if you, so this is when you know it's a complex number. You don't know what its standard form is, but nonetheless, we can find it if we try hard enough. Similarly with division, once again, this is okay, but if we need a simplification, then we need to go through some extra stuff. Extra stuff, and then the trick is here is you may have seen elsewhere a rationalization. The word rationalization, does it sound familiar? Rationalized denominator. Ever experienced it?
So what you do with partial fractions?
Well,
I'm thinking so close.
you were thinking in the right place, meaning it's a trick for an integration trick. Right, so how do I integrate this when I have something as complicated in the denominator? Okay,
By the same over itself,
right, but what exactly? You multiply and divide by what?
the denominator over itself.
No, almost. Same with a
The
plus.
negative of the denominator.
Not negative, no, you replace minus with plus. Okay, so that's called rationalization. Rationalize, the denominator. Because look at it, because the numerator is now the numerator is bad, but denominator becomes good. What's the denominator? What? 1 minus x, right? Okay, so that's literally what it means. The square root is kind of an irrational function that stands in the way of your integration. Okay, so that's a trick that otherwise you might not look up. You multiply by what we call the conjugate. The conjugate of the denominator. So it's not the numerator, it's not the negative denominator, it's the conjugate. So wherever that irrational part is, you replace plus with minus with plus, which produces what these two are. These are the remember the difference. The sum times the difference gives you the difference of squares. So remember this one. Very important one. A minus b, a plus b always comes up with a squared minus b squared. Okay, so that formula comes into play here, and then you can see how I can continue on, right? You can integrate it probably easily. Well, maybe not easily, but it is. You can at least split it like this. And then, well, the first one is easy. The second one might take extra work, but I do seems you think it is might be feasible. So anyway, so that's a trick. Really, let's face it, it's nothing but a trick of integration trick, and therefore not really spend a lot of time, or because it's not really that important. This is also kind of a trick, and it's also called the same way. You multiply by the conjugate. Only what is the conjugate? The conjugate is once again whenever you have the sign between front of the imaginary part is flipped. So if it was a plus bi, now it's a minus bi. So in this case, as you can see, what has happened, denominator is 3 minus I multiply and divide. Right here, this is the trick, almost identical to that one. And what I did is multiply and divide by 3 plus I, and then once again, what happens? Pay careful attention to what's happening in the denominator. It's the same as it happened over here. The formula comes in. This formula comes in. So it comes in here, comes in there, and so difference of squares. And having a square of I, there you go. The I disappears, and then denominator is not a rationalization anymore, but rather what? There is no good word to it. Realization. Not a good word, but it is kind of a realization of the denominator, because it was complex and now it's real, right? It's real now. I squared is 1, negative I squared is 1, and so you end up with denominator simply 10. In which case you can distribute it among the two terms, and there you go. You have the standard form right here. Okay, and so you're done. So that simplification has works its way all the way to the simplest form. So it's a trick, good to know. But or you can take it for on faith. That can always be done. And so when you multiply, add, subtract, multiply, divide complex numbers, you can always carry out that operation through all the way and find the standard form of that complex number. Okay. So, all right. So yeah, that's the point that I was making. Okay, complex conjugate once again. And these are now, let's look at the properties, algebra of real numbers, and now the properties whether we have seen them before or not. Now they emerge as the properties of complex numbers, and they are identical. Okay, so which is obviously good news. So to deserve the word numbers, they have to satisfy these properties at least. So commutative addition, associative addition, commutative multiplication, associative multiplication, and then they distribute it. Okay, so certainly we don't want to go through all these computations, but you can just verify them fairly easily with what we know that these computations are satisfied, and then so that creates a complex number system which looks still complicated, and especially nobody remembers the rules. So what rules? When you do a computation with real numbers, you don't really look at these properties. It's a good idea sometimes go all the way back and put on record what is that property that we're using exactly for this kind of step. So then we can create new type of numbers, and they satisfy the same properties. So once again, going from integers to rational numbers to real numbers, and now to complex numbers. Every time these stay. Okay, so once again, natural, let's say integers, and then to rational numbers, then real numbers, and now complex numbers. The properties remain the same. Okay, so we did already something similar not long time ago. Remember, we did something similar, starting with numbers, and then we discovered algebra of what? Of vectors. That's right. So two-dimensional vectors, they have algebra. It's not the same. And why the difference? There is no multiplication among vectors. Okay, but otherwise, you might also remember there's a rule of thumb. Remember the rule of thumb of algebra of either vectors or now we also putting a rule of thumb for the complex numbers. What's the rule of thumb? Well, treat vectors as if they are numbers. As long as what you've got, your expression makes sense, you can manipulate them as if they're numbers. Okay, so remember certain things you cannot do. For example, you verify that you don't really square a vector. You don't take a sign of vector. There's a lot of things you cannot do. But as long as the expression itself makes sense, you can carry out all the operations as if they were real numbers without actually remembering any of these properties. Okay, so that's the rule of thumb in replacing these 5 properties. Okay, so with the there are fewer properties. Well, actually more properties for vectors than for numbers, even though there's a multiplication of vectors now. So we didn't have to worry about distributivity. So what's the difference? This is the difference. Complex numbers, and I'm talking about and vector versus vectors. I'm talking about vectors of dimension 2 that we concentrated on those, and then it's very much similar, except certainly we added multiplication and division to the mix. Okay, so we were not able to do multiplication of vectors, but we can do multiplication of complex numbers. So nonetheless, the rest is the same. So once again, if you have some kind of complex formula, you can do as if you were whatever you would be doing with with numbers, real numbers. You do the same with complex numbers. So that's the rule of thumb. So that is very important because then we're gonna pursue that shortly is, and the point is that to have the whole calculus done entirely in terms of complex numbers. But that's coming up shortly.
Is there any correlation between like IJK and
No.
I as an imaginary,
No.
completely separate? That's what I thought.
Right.
I know the
Uh,
magnitude.
Well,
of this.
maybe, I don't think so. So this is IJ, right? The
Yeah.
R2, and we name the two basis vectors I and J. In dimension 3, it will be I, J, and K,
Yeah.
right? So we have a similar place, which is coming up. As a matter of fact, if we go with complex numbers, this is what complex numbers. 1 and I. If it makes sense.
Because I was just thinking, because the square root of the sum of the squares would be 1, so it's kind of like a unit, so.
Right, so yes, so you can think of 1 and I as the basis vectors of the complex number system. Like I said, that's a picture. So R2 is two vectors. They happen to be called I and J frequently, but they also E1, E2. So we wouldn't get confused. And then everything can express in terms of I and J as linear combinations of I and J, right? So linear combination over here, linear combination of I and J. So AI plus BJ, right? So that's the plane, Cartesian plane with two-dimensional vectors. Exactly the vectors I'm speaking of here. Okay, and now what's the difference here? It's A plus BI. Okay, so the story is very different, but nonetheless, the name is the same. It's also the idea of expressing the everything on C as a linear combination. Look at it, the linear I could put here A times 1, right? A times 1. Okay, A times 1. So how many ones we've got? That's the real unit, and how many I we've got? The imaginary unit, and they're combined together, producing a bunch of points on the plane. So that's coming up in a minute. And so and then that's the similarity between the two situations. But nonetheless, the differences are here. Once again, multiplication and division. So you can do multiplication and division here, but not there. Okay, so and naturally, if you cannot do that, that's certainly a big a limitation on what you can or cannot do with these algebraic objects. So vectors cannot be multiplied, but on the other hand, you can go with vectors, you can go up with dimension 3, 4, or n, and then everything is the same. So very similar. Complex numbers, however, cannot be easily generalized in the same manner. In fact, here, that's how easy to generalize the 2R3. I add the third vector. Okay, and it becomes R3, right? IJK are the three basis vectors, and you have three-dimensional Euclidean space with all the algebra. Okay, can we do the same for the complex numbers? And the answer is no. It is literal number. The literal answer is no. And some guy actually spent a few years trying to, in 19th century, Hamilton was his name, trying to invent a three-dimensional analog of complex numbers. So complex numbers are kind of two-dimensional, right? So he was trying to invent a three-dimensional analog, okay, and then he discovered that you could, but it's kind of easy to do addition, but multiplication cannot work. Okay, so and then once he realized it's impossible, he then turns out the four-dimensional is possible. Okay, so IJK, literally, I'm not kidding. So the four-dimensional, they're called quaternions, and I can never pronounce it, so let me write it. So that's the generalization of complex numbers. It's actually not three-dimensional, it's four-dimensional. Okay, and then so you have four-dimensional representation of of a four-dimensional analog of complex numbers, so it has multiplication there. So in dimension 3, there is no multiplication, and that's written on his grave apparently, that there is no three-dimensional multiplication, but four-dimensional multiplication does exist. Okay, so all right. Anyway, so let's look at the geometry of complex numbers. So a real part, imaginary part, like I said, it's quite a literally linear combination these are the coefficients, right? This is a linear combination, and these are the coefficients. This is the coefficient. The coefficients are all real, by the way. So, and then there's the coefficient that the real part is the a, and then b is the coefficient of I. So b is also a real number. So b, to be clear, real, and this is real too. So the imaginary part is actually, I'm sorry, no, imaginary part is imaginary, but the coefficient itself, b, is real. Okay, so that's what the imaginary number is. It's I multiplied by a real number. Okay, so standard form, two complex numbers are equal if only both real and imaginary part are equal, just like vectors. Okay, so this is how we can write it. So it's sometimes convenient, even though not a big deal. This is the where geometry comes to start to appear. We realize that the real imaginary numbers, the real and imaginary axes have a point in common. That's the zero, and therefore that's how they should be attached to each other. Okay, so like this. And then there is the rest of them. Where's the linear combinations? They're all here, and so we realize that we actually do have a plane of real imaginary numbers if we're just willing to combine them together, just like we did in two-dimensional case of vectors. So one axis, the other axis, and then every complex number, such as this 2 plus 3i, is represented as a point on the plane. So this is called the complex plane. And then once again, the real axis, and that's real axis, is the horizontal, and the vertical is the imaginary axis. And then the whole plane is then filled with complex numbers. That's what make them complex. So real number, there's only one line, and that's what we have been doing for forever, including all the calculus. All the numbers are real, and then we sort of found more numbers in the extra dimension beyond this. So if you, for example, you have a graph like this, x, then this is the real axis. Okay, so if you have a function, then you might ask yourself, what if I expand beyond like this? And in the imaginary domain, in the complex domain, complex plane is actually, so that x-axis is actually only a slice of that little line within the complex number plane, and therefore every function, for example, can be easily thought of as if it has a complex. It is complex. It has complex input and complex output. Okay, so for example, y equal x squared. Well, from now on, x does not have to be real. It could be complex. Okay, so literally then in this case, the domain, the complex plane is the complex plane is the domain of the function. Okay, so everything else lies above. Okay, so imaginary numbers. By the way, the fact that they're perpendicular here might be important, but at this point it's not. So hypothetically, I could have my x's like this, and that would be just fine. Once again, there is no trouble to do it like this. So the grid that is sloped. Okay. So all right. So once again, let's put this to bed. The matching between C and R2. Okay, so complex combination of two real numbers. This is I and J. Let's say E1, E2. So there will be no confusion here. So E1, E2. Whatever they stand for, the nature doesn't matter. And this is the unit is 1 and the unit is I. Okay, so like these are the axes. And the axes follow the directions of two basis vectors. And here the things change, but the names change. The nature of the vector algebra remains the same. So whatever addition we did with the vectors in dimension 2, we still do them with the complex numbers. We just now, in addition, we have multiplication. Okay. So all right. So this is the important to have the to imagine what the conjugate numbers look like. They have the same exact real part and opposite imaginary parts. Okay, so a plus bi, a minus bi, these are the two numbers that are conjugate. Obviously. So in other words, we are looking at I plus a plus or minus bi, the conjugate pair. And where else did we see this a plus bi? Where did we see plus or minus? Just now. The quadratic formula. Right, so then that we're going to be seeing every time we have a quadratic equation, and quadratic formula applied or not, the answer is always a conjugate pair, unless the answer is real in the first place. So okay, let's carry this out. Okay, so we classify quadratic polynomials. Okay, so that's what the quadratic polynomial looks like. In the ODEs that we have been doing, with the a is equal to 1, so we can concentrate on this one much easier, so that the coefficient of x is actually 1, and so also we don't have to worry about a, b, and c having the same letters. Okay, so then we're looking at the polynomial that is x squared plus bx plus q. Okay, as long as a is not equal to 0, then we can easily transform from one to the other. Then this is the quadratic formula right here. Okay, the discriminant is still visible. This is the discriminant is the p squared minus 4q, as we reviewed not long time ago. Okay, and then that is the number that could be negative. In which case you end up with square root of a negative number. In which case you end up with an imaginary number in that where the square root is. There will be an imaginary number. So that's the main classification here, is this of quadratic polynomials, x-intercepts. Do we or do we not x-intercepts? The x's that we drew here is the real one. This is why this is not the complex plane. This is what we're looking here, not the complex plane. Unfortunately, plotting polynomials that happen to be complex, think about it this one. Now we imagine now x is complex, yes. So then so is y. So is y. Okay, so think about this. Okay, so if we were to move on from real to complex numbers and we concentrate on nothing but the quadratic polynomial, then things become really complex. No pun here, really. So when x is real, means that the domain is real, but the codomain is, I'm sorry, complex, and so is the codomain, right? So x is complex, it's a plane, and the codomain in another complex plane. What's the total dimension? 0.2, it's 4, and you cannot plot the graph of this very simple quadratic polynomial. You can't plot it because the graph lies in the 4-dimensional space. So that really takes the wind out of our sails. If we want to do calculus, we cannot plot graphs anymore in the complex if we decide everything is complex. So that big trouble. So that's why. So not, we have to actually go back to real and just assume that the complex stuff happening somewhere else. Okay, so because we cannot visualize the graph of a simple function as a quadratic polynomial. If the inputs are complex, then so are the outputs, and you have the total of 4 dimensions, and you simply cannot plot. Okay, so then if we go back to real, this is real, everything is real. Y is real, this is x also real. Okay, and so by the way, to make a distinction, frequently we replace x with z, so that when we use x, we think real. When we use z, we think complex. Okay, so this is the real, and then the polynomial. So this is all kind of pre-calculus business. And then it could, if it has a 2x intercepts, we have 2 real roots. That's when the discriminant is positive. This discriminant is 0. Okay, so it touches, and this discriminant is negative. Okay, and then which means that we do not used to abandon this to say, well, there are no real roots and let's move on. Now we don't do that anymore, because we know we have complex numbers available. And then yes, indeed, there will be 2 answers. and the two complex roots. Okay, so so in a way, there are always two roots. This they just counted twice because it is a complete square. Say, for example, if this is 2, then x minus 2 squared. So 2 is a twice counted root. Okay, so these are two different ones, 1 and 2, complex 1 and 2, they counted twice. And this one is 1, but it counted twice because it is actually part of a complete square. Okay, so that's the formula. Okay, so I take discriminates, and so it determines whatever is happening. Okay, so then these are the three possibilities, as I pointed out. Depending on the value of d, you could have two real roots. If it's positive, it's 0, then you have one root appearing sort of twice. And complex, you have two complex conjugates because of the plus or minus, which is right here in the quadratic formula. You have plus or minus, the rest is the same. So it is then square root of negative d. And remember, d is negative, so negative d is positive, and so this is then we have classified things, and this is the real part, and this is the imaginary part. This is the real part, this is the imaginary part. Since they are the same up to that plus sign, they are conjugate of each other. So then this is what it looks like this, as I just pointed out, these two x1 and x2. You're probably once again better off calling them z's. So this is say z1 and z2. Okay, so they conjugate. Okay, so there is a relation between them. So in order to make so here's the picture, slightly better picture of what we see, what I just showed you, and there is a point. Let me quickly jump back to differential equations, or rather to the linear algebra. Remember linear algebra and what happens when our eigenvalues are complex. Okay, so typically, so if the discriminant is positive, you have two different unrelated eigenvalues, and remember what they're referring to. They will be stretching. Okay, so if it's positive, it's stretching. If it's if it's negative, there's also a flip there. Okay, and now the d equal to 0 is complicated case, edge case between the two. And here is you can actually point out what's what, and so if this is my eigenvalue, then A is responsible for the stretch, and B is responsible for the rotation. Okay. So if you remember the very last theorem that we had about the eigenvalues and what they tell us about the behavior of the linear system of differential equations, we had that that case when discriminant is negative. Okay, discriminant is negative. Then we described the behavior of the linear operator as the one that stretches uniformly. Okay, the uniform stretch combined with rotation, that's what it is when d is less than 0. And that's you can see that there are actually two roots, but because their real part is the same, well, that's why the stretch is actually uniform in whatever directions are. The stretch is uniform, and then b, like I said, b is responsible for the rotation. So meaning that when b is equal to 0, then there is no rotation, and we are back to the case when we started with, when there is just two disproportional stretches in two different directions along the eigenvectors. Okay, so just to point out that why we do it, but we stick to once again the idea of classifying the quadratic polynomials for now, nothing else. So, all right, so here's an example, just running through the computation. So this is my real value, by the way, real coefficients polynomial. Nonetheless, it produces complex numbers. If you plug in complex numbers, it will give you complex numbers, right? So, and we're looking for whatever numbers x will make it into 0. Quadratic formula applies perfectly well. In this case, it actually happens to be discriminant is negative. We know that ahead of time that we're going to have as the answer already two complex conjugates. And then you just apply the formula, the quadratic formula right here. And then you have, as you can see, -1 plus or minus square root of 3 or 2i. Okay, so once again, so you can roughly imagine what they look like. So the real part is -2, so this is -2, and then you jump up and down roughly, one of these will be here. And the other one is here. Okay, so these are the, no. They're symmetric relative to the x-axis, to the real axis, right? Okay, so that's how we do kind of a pre-calculus, but with complex numbers. Okay, pre-calculus meaning, or even not even pre-calculus, like high school algebra, well, where do you see quadratic formulas for the first time? So that's the same thing, except now we're doing it with complex numbers rather than just real numbers, and so surely it's hard to plot. It's hard to plot, right? So where, if this is my complex plane right here, where is y? Where is y? So these are the axes, right? The plane of axis here. Where is y? Out the third dimension. And then, and I'm being generous here because actually there are two dimensions here because y is also complex. So try to imagine two planes, but not intersecting. They only have one point in common. So that's the problem. Remember how it works out. Okay, so you can see how gradual transition is, just in case here, as you move the quadratic parabola of the quadratic polynomial. It has two solutions, one solution, and zero solution. So as that last coefficient grows, that's what happens. Okay. So we already have discussed that. So I'll skip the proof. But the main classification is that this is the main part. Two distinct real roots when the discriminant is positive, equal real when the discriminant is 0, complex conjugate when the discriminant is negative. That's the classification, really. The main thing for us to know. Okay. So just the visualization of those three cases. Okay. 1, 2, 3. Yeah, so these are 1, 2, 3. 1, 2, 3. They are visualized here. Okay, and these are the first one and second one. You could put that's the real axis, and so the two roots lie on the real axis. And there could be one, but still on the real axis. And then once they become complex, they actually split, but only in a kind of a fashion. They split not in arbitrary way. They have to be always symmetric. Okay, so and then okay, so the real parts. You can see the pictures probably. This is especially for the differential equations case. This is really what we care about. That in case the discriminant is negative, we end up with two complex conjugate roots. And then we'll just talk about when time comes how to interpret that complex number that we have found as a root, how to interpret it, and what does it tell us about the linear operator, and then in turn what it tells us about the system of differential equations. Okay, so skipping. Okay, so the complex plane is the Euclidean space. I already talked about that, so this is pretty much done, meaning that complex. Now, as far as the addition of complex numbers, the addition of vector is the same. So that's the easy part, and so literally that vector AB is written differently as A plus BI because the real axis is the horizontal imaginary axis for vertical. And so then you execute your addition as if you were executing addition of vectors. So keep the components separate. You do the horizontal components separately from vertical components and then combine them together and just leave it. Okay, so there is no challenge whatsoever. Is even I write it here. So the second line is the familiar vector addition that we've done before, and the first line is the addition of complex numbers. As you can see, they repeat themselves very much in a manner that is very familiar and pretty much identical. Okay. So this is addition of vectors. Once again, makes no difference. You do addition of vectors or addition of complex numbers. So in other words, the addition of complex numbers is vector addition. Okay, so these are vectors, but you can think of them as well as this is what is it, 3 plus I, and this is 2 plus 4I. Okay, and then the result here, I have 5 plus 5I. Okay, so it's the same thing. As long as we don't multiply, we're fine, and we think of complex numbers as vectors. There's no difference. Same with scalar multiplication, meaning multiplication by real numbers. Okay, so once again, component-wise, do it in the same exact manner. This is more important, and that is the interpretation of complex numbers in terms of the angle. And so here are some things that remember that when we reviewed parametric curves, remember that comes into play very much significantly here, because now we don't want to concentrate on the xy plane anymore in x and y coordinates, but rather we concentrate what amounts to the polar coordinates. Okay, so then we can express our complex number. This is still point xy, but it can be expressed now in terms of sine and cosine of the angle, right? So if the distance to the point xy is r, okay, so then the components of or coordinates of that vector of these points are this is x is r cosine theta, and this is y equal sine theta. So then by that computation that we know, now we have a new representation of a complex number in terms of, once again, not Cartesian coordinates, but rather in terms of polar coordinates. So theta is the angle and r is the distance. Okay, so it's r cosine theta plus r sine theta times I. Okay, so that comes up frequently, and especially when you do some certain types of algebra, and that's why trigonometric formulas rather come into play very significantly. So sum of angles, cosine of some, sine of some, and so on. Just the array of formulas is just so dazzling. Okay, so all right, and then we start towards the calculus of complex numbers. Step number one is a sequence. For example, a sequence is of complex numbers is nothing but sequence of points on the plane. Okay, as long as we, once again, the only operations that we execute are addition and scalar multiplication, then this is just a sequence of points on the plane, and you can interpret them as vectors. You can interpret them as point. You can interpret them as complex numbers, as long as we stick to dimension 2. That's what it is. Now, nothing complicated, but you already can ask the question. The correct question here is, what is that? What is this? This is supposed to be illustrating the picture. What is the picture supposed to illustrate?
Spiraling in.
Can you be more specific? If this were about calculus, what is that we're talking about?
The limit 0.
The limit, right? It is. We are speaking of the limit. So in calculus 1, the convergence is kind of one-dimensional. So you stay within the line, and then you jump left and right, and then there's a convergence somewhere. But here it is two-dimensional, so convergence is on the plane, but nonetheless the idea is still the same. The distance has to be going towards 0. So this is what we're talking about. So 0 is the real number. So this is, you can still think about this as points, but if we were to speak of the calculus of complex numbers, that's what we would be doing. We would be considering convergence of points on the plane, and then we can guess, if you remember a little bit of calculus 3, then we can do them component-wise. So convergence is component-wise convergence. So what does it mean for the sequence to converge to 0? The answer is very simple. These two each go separately towards 0. Why? Because 0 is 0 plus I is 0, which means that the real part is 0 and the imaginary part is 0, which means that the real part has to converge to 0, the imaginary part has to converge to 0. Okay, so component-wise convergence. And so that's, once again, the same idea. Everything that used to be one-dimensional, whether if you have not, faced this in calculus 3 yet, then this is the time, the idea is still the same. So you have points on the plane, and then you used to zoom in on the graph of a sequence, for example. We do not have that luxury because there's no extra dimension here. So we have a sequence of complex numbers, the dots on the plane, you keep zooming in. And then, and the idea is that no matter how close you zoom in, the tail of the sequence will be within your field of vision, right? So you can see how I'm zooming in. So I have a sequence, and then there is a suspect limit, the red dot. I zoom in on it. It seems to contains only one point, but then turns out there's a bunch of points within that. That's like this. It's still more points here, and then you zoom in some more, and then we still infinite process of zooming in. Every time you'll have infinite many infinite the infinite tail of the sequence is still in your field of vision. That's what informally speaking, convergence is all about. So that's how you explain it, how you visualize it, but ultimately how you actually carry out computation, you do it component wise. This is if you want a convergence of vectors. That's a convergence of vectors for you. Okay, so as I said, you can do it component wise, but really what we speak of, we borrow the geometry. Once again, without referring to any more complex algebra of complex numbers, we are borrowing geometry from R2, Euclidean geometry, and so we can measure distances on that plane. And so we have this. Remember what this is? This is the norm of your vector, and in other words, the distance between the 2 points, and that is supposed to converge to 0. Okay, so here it was, we're converging to 0, so that's kind of obvious, but this is what we are. Picture here, like this. So there's a point here somewhere we're converging towards some kind of a z. So this is zk, and it converges to z. And then how do we know? We take the distance from zk to z. Okay, and that's what's so great about the distance is it's nothing but distance is a real number. And so then the idea here is to convert something that we just introduced, convergence, the idea of complex sequences and complex convergence. We reduce it to that of real numbers. Okay, so the geometry of the complex plane is real in the sense that distances are real, right? So like I said, if we put equivalence between C and R2 in that sense, in terms of distances, then that's what this is. That's the distance of R2, and of course it is a real number. And then so we speak of nothing but sequence of real. This is the sequence of real numbers. So then the familiar calculus 1 kicks in. Okay, and then so the distance is supposed to converge to 0. We apply whatever we know about convergence here. So all the rules of limits and later on derivatives and integral come into play. Notation is exactly the same. Either it is LIM or it is an arrow. It's the same notation as before. The terminology is exactly the same: convergence, limit, divergence, and so on. Even though, as you can see, the behavior is way more complex because it could have a spiral. It could spiral is one typical example that you don't see. It can run away to infinity, but not straight. Maybe spirals actually goes in the opposite direction, so that's also a possibility. Okay, so a sequence can have only one limit. So all the theory mimics the theory of real numbers. And so, for example, sequence can have only one limit. Okay, then we can that's the explanation of divergence to infinity here. Component-wise convergence, as I said. So sequence of complex numbers converges if and only if there's a convergence of its real parts and its imaginary parts to the real imaginary parts, respectively, of the limit. Okay, so once again, it's really not complicated if you get used to it, especially if you have seen anything calculus in dimension 2. And then some rule for complex sequences, the constant multiple rule for complex sequences. The pictures are surely much more interesting. So what this supposed to show? two sequences, okay, the red and blue, two sequences, both of them converge, right? Specifically the spirals converging, okay, so, and I have a point here, I have a point there, and then I add them. Add what? I add sequences, and then look for the limit of that new sequence, or I find the two limits first and then add them together. Remember that diagram? I have this diagram here, I have a diagram here. But it turns out it makes no difference, the result is still the same. So so do I need to explain the diagram here? Two sequences, the two smaller sequences, they added together to produce the green one. And because both of those two are convergent, the new one is convergent too. Okay, so if you put it in words, the theorems of complex calculus are identical to the ones of real calculus. So two sequences converge, then so does their sum. Okay, so it actually let me, C is equal to right here Cn is equal to an plus bn. So the green one is the sum of the blue one is the red one. Okay, and then the issue is there are three limits to worry about, and what's the relation between them? And the answer is once again they add up together. Okay, so one limit here, the other one limit is there, and then the sum is right here. So if it looks unusual, then the formula, look at this. This is virtually not virtually entirely identical theorem itself. That except for the word complex over here, it's actually the same exact theorem as you see in calculus 1 or calculus 2. So sequences converge, so does their sum, and then the limits try to use this to say it in words. The sum, the limit of the sum is what? The sum of the limits is. You can say that about numbers, numerical sequence. You can speak of them as about vectors too, if you're doing vector calculus, or you can now say about these as sequences of complex numbers. So another way to explain it is once again the order of operations. It is so I have two sequences zk uk, and then I could go with their limit first, producing say z and u. Okay, and then I can do addition if I add them together like this. So I have zk plus uk, and horizontal is the limit. Okay, so here I have then limit of zk plus uk if I go horizontal, and if I go vertically like this, right? So that's it. I have z plus u. Okay, so limit then addition, or addition then limit, the end result is the same. So there are two routes, left and down, or down and right and down, or down and right. The end result is the same. Okay, same. So once again, it all comes from calculus 1, the same idea. Well, the same here. Once again, I can write it in words. The rather a constant multiple, the limit of a constant multiple is what? The multiple, yes, of the limit. Once again, this is about words. The words apply to R, Rn, or vectors, and now to the complex numbers. So just to point out that everything works out for complex numbers, as if domains and codomains are now complex rather than real. We have the algebra of complex numbers, so we can do domain and codomain. That nothing changes. We can add and functions, for example, and then we also have the geometry in domain and codomain, and therefore we can speak of things such as convergence. You remember, you have to measure things in order to know if there is a convergence or not. And then, so we can speak of convergence, and we can speak also of continuity, for example. So we would take far from this to speak of complex functions being continuous. And then once we speak of continuous and we understand limits, we then move on to the to derivative and the integrals too. Okay. And as I said, the words are very much the same. So, so as I just said a minute ago, that our C is Rn, C is R2, but it's not just R2 because if we throw in the multiplication of complex number. Okay, so the difference between complex numbers and vectors, here it is. So as I said, these two properties right here, these two properties are about addition and scalar multiplication, and then they exist with vectors. Okay, but what exists with numbers, real or complex, it does not exist with for vectors. That's multiplication, the regular multiplication of complex by complex. Okay, so so what is the meaning of multiplying by a complex number? Probably worth examining before we do any kind of calculus related things. So multiplication by a real number, whether it's R2 or it is C, is a stretch, a uniform stretch, right? So vectors, you multiply by 2, everything becomes 2. What if I multiply by a complex number? What's the meaning of multiplying by I? Okay, so it does something to the plane. Okay, so if we look at it, what happens? I start with 1, multiply by I. This is I. I multiply by I one more time. I have -1, right? I multiplied by I gives me -1. I multiply by I one more time. I have -5. Multiply by I one more time, and I'm back to 1. -I times I is 1. So I carried out 4 multiplications. So this is the way, this is the 1, 2, 3 multiplication by I. Okay, and every time the same thing has happened, there is what happened is a rotation by 90 degrees. Okay, so that's the very important thing to understand about complex numbers, what they do to the plane to when we multiply by them. So the simplest complex number that's not real is I, the imaginary unit. So multiplication, as I said, by a real number gives you a stretch. And this is by imaginary numbers, it's something entirely different to look at it. It's actually rotation. So is there anything that can be more different than that? And we know from linear operators analysis study that they are opposite things. Stretch, every vector is stretched, right? That's if it is a uniform stretch, then every vector simply keeps its direction and just becomes longer or shorter. Okay, so that's, and then but multiplication by an imaginary number is a rotation. So stretch, shrink, directions hold, right? That's the thing. That's what stretch is. Direction remains the same, and rotation is the exact opposite of that. Everybody rotates, and by what turns out that multiplication by I rotates every number by 90 degrees counterclockwise. Okay, so then if I were thinking of this as a linear operator, I would have this, right? Remember, rotation 90 degrees, 90 degrees, that's what the matrix is. So it is interesting that actually multiplying by one single complex number actually produces a linear operator. We're not going to go in that direction. We would just want to see that indeed the meaning of multiplying, the meaning of this algebraic operation on complex numbers. So 1 times I is I, multiply by I one more time, you have I squared, which is -1, then multiply by I again, I have -I, multiply by I one more time and have 1. And so in multiply by I 4 times, I come back all the way back to 1. Okay, so you can demonstrate that it's exactly the same story if you multiply it by any number. So any number, a plus bi, I multiply by I, what happens? So z is a plus bi, I multiply by I have iz. Let's carry out that multiplication. I have ai plus abi. Okay, I di, which is it's up to negative b. So I end up with negative b ai. Okay, so in other words, a plus bi becomes, look at it, negative b plus ai. So remember, a is there's a real part, there's a complex part, but they have been flipped. They have been flipped with the negative sign, which is, as we know, remember when we study linear operators, that's what rotation 90 degrees does. It changes x's and y's with the negative sign. Yeah, so all complex numbers are rotating 90 degrees. Okay, so that's the operation. And then it just the question becomes, what are the complex? Every complex number when that is not real will produce rotation. Okay, so for example, more complicated example, this is the just multiply two numbers, you carry out this simplification as we have done before. Where the rotation? Well, let's just plot what we have here. So the two numbers, we have 1 plus 2i, one complex number, the other one is 2 plus i. Let's see what has happened here. So these are the two numbers, u and v. Okay, uv is over there, it is 5i. Okay, and then you can tell what has happened to the time, but you can see that rotation is so 2. Look at this. This is 2 is the stretch. So rotation 90 degrees. I gives me 90 degrees rotation, and 2b gives me the stretch. And you can totally see it right here. So what has happened to the vector u? It's been stretched by 2, right? This is my stretch, and then it rotates 90 degrees. Okay. So I'll stop here and I'll see you.